Welcome back, ladies and gentlemen, to our continuing study of two-dimensional kinematics. You might consider today's topic the main course of this unit. We've been studying vectors. Vectors are tools to help us analyze two-dimensional motion, and the most common type of two-dimensional motion that you'll come across is projectile motion, right? Hitting a tennis ball, shooting an arrow, throwing a basketball, lots of everyday activities, fun ones at that, involve projectile motion. So come along with me as we take our vector knowledge and apply it to projectile motion. Let's get started. First, we should define projectile motion. Let's define it in light of free fall. You see on the screen the definition for free fall, which is an object moving only under the influence of gravity, right? So if I take a ball and I drop it, right, that's going to be free fall, okay? Or if I throw an object up in the air and it comes back down and the only force on it is gravity, that's considered to be free fall. Now, in these cases, we neglect air resistance. Okay, so projectile motion is pretty similar to free fall. It's actually an object in free fall, but it's given an initial velocity, right? So it's instead of an object dropped, right, it's an object that's going to be thrown like some sort of initial velocity, right? And it's gonna follow a parabolic path, right? It's not going to follow a straight line path. So in this case, right, the acceleration that it experiences at every point here would be oops, that's supposed to be straight down. Be straight down, right? Because the Earth's pulling it down, the Earth's pulling it down. Those should be equal-sized arrows, right? The Earth's pulling it down constantly the whole time, and that's what's making it go in its parabolic path in the first place, right? Remember Newton's first law, objects in motion continue how? In a straight line at a constant speed, right? This object's not doing that because it's under the influence of the force of gravity, experiencing a constant downward acceleration. So projectile motion is simply an object in free fall with an initial velocity in two dimensions. All right, let's go to the next screen. And let's break down the projectile motion a little bit more. I'm going to draw two different examples of projectile motion for you. The first here might be like a football throw or a soccer kick downfield, right? Something like this. Okay, that's supposed to be a parabola. It's a pretty ugly parabola. How about that? It's a little better. Okay, let's take a look at what these motion graphs would look like. But we're going to look at it from two perspectives, right? Up to this point, you've only done motion graphs in one dimension. But let's break this motion down and see what it would look like in two dimensions. So let's see here, the x direction graph. So just to illustrate to you what's going on here, the x direction graph is actually going to look like this, believe it or not. Okay, and the x velocity graph looks like this. I'm just going to draw them in and let your sharp little minds feast on this for a little bit, okay? And then while you're thinking about that, I'm going to come over here and do the y direction. So notice what this tells us. In the x direction, right, there's no push or pull in the x direction. And horizontal velocity, whatever it was when it left the hand or the foot or whatever projected the object, okay? Horizontal velocity stays constant in projectile motion. And there's no acceleration in the x direction, right? There's no push or pull in the x direction. The only push or pull is in the y direction, which is why you see a constant negative acceleration on the y side and a parabolic motion on the y side. So notice that the acceleration and the force causes accelerated motion in the y direction, but there's no accelerated motion in the x direction. All right, another version of projectile motion uses a different color here would be a horizontal launch, and that would look, say you're on a cliff here. Okay, that's down here. Let's say I just threw something off the cliff, right? It'd be horizontal launch like that. The graphs are going to look pretty similar. Okay, in fact, they're going to look almost the same. This is assuming that I threw. I'm just going to draw these on top of each other here. Okay, the only difference is over here on the y side, this graph would look like this. Okay, the velocity graph. I started from zero. When you launch something horizontally, it doesn't have an initial y velocity. Okay, but all the other graphs would pretty similar. So the green one on top of the yellow one there for acceleration, and then I guess the trajectory would look slightly different depending on where you put your origin here. the trajectory would look, something like this or something like this, depending on where you put your origin. All right, let's go to the next screen and let's break down projectile motion into its different versions. So horizontal launch, right? I've mentioned this already. That's going to look like this, and that's its distinguishing characteristic is that there is no initial vertical velocity. Okay, I can write that down here like this, Vy equals 0. Okay, that generally tends to simplify your problem solving. The second type would be the angled launch on level ground, right? And I gave you this example already as well. Okay, here in the middle, right? That'd be something like this. Okay, where you start and you end at the same height. Now, in this situation, it's a little more complicated because you do have initial y and x velocity, but because you land and start at the same height, there's a certain symmetry there that you can use in your favor. And there's also something called the range equation, which gives you the range. Okay, right? This would be considered the range, the horizontal distance here. There's a range equation that we can derive. You may have seen it last year or previously. We're going to derive it using calculus in class. But the range equation applies only to angled launch on level ground. Okay, and then finally we have here on the right, we have the most complex kind, which would be angled launch on uneven ground, right? That could be like this. Okay, let me use the dotted line. That could be like this, okay? Or it could be like that, right? Initial downward angle like that. So those would be the most difficult, that would be the most difficult kind. All right. One more thing I'll mention about angled launch, okay, both with level ground and unlevel ground or uneven ground, is that since you have an initial x and y velocity, for example, I can draw it here. Let's see, it looks like that, okay? Maybe we'll do that green arrow. No, white arrow's good. Okay, so if you you're actually going to use a little trig to break down that velocity. So if I take that velocity triangle, I'm going to draw it up here like this, okay? Often you're given an initial launch velocity, like at a certain angle, okay? So what we can do here is we can break this two-dimensional vector down into two one-dimensional vectors, right? Where this would be some angle theta, okay, that would be your launch angle, and then you would use your trig, okay, to get to the components. So this would be V sine theta, okay, and V cosine theta, and the diagonal is V. That's the initial velocity. So when you work in the x and y direction, you have to break that two-dimensional velocity down into its two one-dimensional components. Last thing I want to talk about is just some basic tools for setting up problem solving for projectile motion. You see on the next screen here, okay, the following. I strongly suggest all students take the whole width of their paper and draw it into two columns. Because when you work on projectile motion, you can only work in one dimension at a time. And it's very, very important to keep your x quantities, right, your horizontal quantities, separate from your y quantities. So I'm going to pause for a minute and I'm going to write some things in each column and come back. You see on the screen the constant acceleration equations. Okay, projectile motion is a constant acceleration situation, right, negative 9.8 meters per second squared on Earth. But what I'm trying to visually demonstrate to you here is that the constant acceleration equations apply separately to each dimension. You can use the same equation two different times in the same problem, once for the x and once for the y. And that's why it's so important to keep your x quantities separate from your y quantities. Now, you don't have to write these, 6 equations or these 3 equations twice every single time. I'm just writing that to demonstrate to you that you have these 3 tools available to you in every single projectile motion problem. That's why it's so important to use the width of your paper, divide it in half, and keep your x separate from your y. All your x work on the left, all your y work on the y. Now, what you will have in every single projectile motion problem is the same starting variables. So I'm going to pause again and write those out. And these you do want to write down every single time because you need to account for them. On the screen, I went ahead and sketched a problem in the upper left-hand corner. Okay, it's a horizontal launch problem. and the object's launched at a height h above a cliff. So this brings to light a few things that you need to do before you can identify the 6 variables in each direction. You need to have a sketch and a coordinate system. Okay, a coordinate system involves identifying an origin and identifying which way is positive. So I've identified an origin with the green dot. It's the base of the cliff. You could also choose the launch height. That's another acceptable choice for the origin. Okay, your choice, you're the physicist. I just chose the base of the cliff. And then typically on a piece of paper, to the right is positive and up is positive. And you indicate that by drawing this little coordinate system looking thing right there. That tells us which way is positive. Okay, so in each situation, you should be able to identify these 6 variables and figure out which ones are missing. So watch how I do this here. In the x direction, I start at the origin, and that will be my range, right? The horizontal distance, the range. Okay, I might be given that number, I might not. But watch what else I know. I know the acceleration is 0, right? We've talked about that already. And that's all I know typically on a horizontal motion problem. On the y side, right? I know this. Okay. See if that makes sense to you. Now, this happens to be only for horizontal launch, right? For a non-horizontal launch, this wouldn't apply. But for horizontal launch, I know the vertical velocity in the beginning of 0. All right. Now, notice that there's only one variable that you find on both sides, the bridge between the 2 dimensions. Okay, and that is the time. Okay. So the most common approach here that you take to projectile motion problem solving is you identify on which side is my unknown. What are they asking for, or asking me for, right? So for example, let's say they wanted to know what this was here, okay? Typically, if your unknown is on one side, you're going to start on the other side. So if you see that your final unknown is on the x side, you would actually come over here to the y side and see if you could use one of these 3 equations to solve for time, right? Because time is your bridge. You solve for time, and then whatever you get for time, you can then take that number and bring it over and use the x side equations to solve for your final answer. Now, final note here, notice that the x side equations, since there's no acceleration in the x direction, vi and v are the same. Okay, that makes this equation go away completely. Okay, because there's no acceleration. Okay, let's get a little messy. But basically, because there's no acceleration, these 2 are equal. Okay, and same here. If you go down to the 3rd equation, that goes away. There's no acceleration. Vi equals v. You already know that. And then over here, okay, the 2nd equation, since there's no acceleration, all you're left with is this right here. Okay, that is the only equation that you'll ever use on the x side in projectile motion, because there's no acceleration in the x direction. All right, there you have it. That's the basics of projectile motion. In the next lesson, we'll actually solve a projectile motion problem.